Have you ever fed an AI your dream itinerary, only to watch it completely unravel the moment you step outside? You ask for a 3-day trip, and the model hands you a schedule that ignores actual transit times, skips over attraction queue lengths, and routes you backward across the city for no reason. It looks perfect in text, but it's useless in practice. Until recently, we didn't have a rigorous way to actually test if AI travel planners were solving a real optimization problem, or just generating plausible-sounding text. Most existing benchmarks only check surface-level constraints. Did it stay under budget? Did it hit the requested number of cities? They completely miss the multidimensional chaos of real-world travel. That gap is exactly what a new research team set out to close with TravelEval. Instead of simple pass-fail checks, TravelEval evaluates AI-generated itineraries across 6 distinct, quantifiable dimensions. First, accuracy and compliance verify that the model isn't hallucinating attractions or violating hard constraints. Second, temporality measures actual time utilization, factoring in transit durations, dining windows, and predicted queue times. Third, spatiality evaluates geographic routing efficiency, penalizing illogical backtracking and measuring actual path distance versus optimal routing. Fourth, economy tracks how well the budget is distributed across transport, lodging, and food. And finally, utility measures preference alignment, assessing whether the final plan actually delivers the experience you asked for. To make this evaluation possible, the researchers didn't just rely on static datasets. They built a high-fidelity simulation sandbox. They integrated precise, dynamic pricing for thousands of hotels, real-world high-speed rail and flight schedules across 10 major metropolitan areas, and trained a predictive model to estimate attraction wait times based on temporal features like day of the week, time of day, and seasonal demand. This transforms travel planning from a pure language generation task into a constrained, multi-objective optimization problem. They then ran this simulation across 12 popular foundation models and 3 distinct prompting strategies. Direct generation, where the model outputs a plan immediately. Chain-of-thought prompting, which forces step-by-step decomposition. And a reflective approach, where the model generates a draft, critiques it, and self-corrects before finalizing. The test cases were deliberately scaled from baseline constraints to highly complex multimodal preference sets, simulating everything from simple point-to-point trips to tightly constrained itineraries with dietary restrictions, transit preferences, accommodation requirements, and specific rhythm targets. The results exposed a fundamental bottleneck in how current architectures handle planning. Budget compliance was consistently the weakest dimension, with models either blowing past limits or aggressively pruning high-value activities just to satisfy a hard cap. But the most counterintuitive finding was what happened when we scaled up reasoning complexity. Adding chain-of-thought steps or self-correction loops didn't improve the itineraries. In many cases, it actively degraded them. The researchers identified a cognitive overload threshold specific to constrained planning. When you feed an LLM a dense web of conflicting preferences and force it to maintain a long reasoning trace, the attention mechanism gets saturated. The model loses track of global constraints, starts prioritizing local coherence over global optimization, and the quality of the route actually drops. It's not that the models are incapable. It's that their autoregressive nature struggles with backtracking and long-horizon constraint satisfaction without explicit structural guidance. Tool-augmented agents, which plug into live APIs for real-time pricing and schedule lookups, did solve the factual grounding problem. Budget accuracy improved significantly when the model could query live data. But even with perfect information, these agents still struggled with spatial routing efficiency and overall experience utility. This tells us that the bottleneck isn't just about access to data. It's about how these models fundamentally process multi-step, real-world optimization. TravelEval gives us a much clearer map of where AI planning actually stands. It highlights that building a truly reliable travel agent requires moving beyond prompt engineering and toward architectures that can natively handle temporal scheduling, spatial routing, and preference trade-offs. If you've ever watched an AI itinerary collapse under real-world friction, you now know exactly why it happened. And as benchmarks like this push the field toward rigorous, simulation-based evaluation, we'll finally see planning models that don't just sound coherent, but actually function when you pack your bags.